So this is 2.4, linear inequalities and problem solvings. And we're going to go over our first objective, which is using interval notation. Wrong. Here we go. So actually, let me first just introduce you to some symbols that denote linear inequalities. So these in yellow are symbols, and of course A and B are any two real numbers. So in inequality symbols, they're used to express mathematical statements, and they're statements, and statements can be either true or false. For example, if I say today is December 25th, that's a statement that actually happens to be false. But today, if I were to say today is August 20th, that statement actually happens to be true because the day indeed is August 20th. So you've probably seen these before, but I'll go over them really quickly. This is read A is less than B. This is read A is less than or equal to B, and it means that A is less than B or A is equal to B. So it's two statements, either A is less than B or A is equal to B. A is greater than B. A is greater than or equal to B. So let's give some examples of these statements really fast that are true, and maybe one or two that are false. So if I say A is less than B, minus 3 is clearly less than 10. That's a true statement. A is less than or equal to B, minus 3. So this is read minus 3 is less than minus 3, which is false, or minus 3 is equal to B, which is true. So this is a true example of that statement. A is greater than B. 4 is greater than 3. 4 is greater than 0, greater than or equal to 0. In this case, 4 is not equal to 0, but 4 is greater than 0, so it's true. So all of these are examples of true inequality statements. Here's an example of a false one using greater than. 4 is greater than 5. So this actually happens to be a mathematical expression expressed using an inequality that happens to be false. And of course, what we're looking for are values that make them true rather than false. So our next concept, which is here, the linear equality in one variable, but I went ahead and copied that down here, and I copied it wrong. Hold on, after all this prep work, I still did it wrong. That shouldn't say linear equation. That should say linear inequality. I get it right down below. You say linear equation so many times, it's really easy just to go back and say what you're used to saying, a linear inequality. A linear inequality in one variable, such as the variable x, can be written in the form. It's not always written in the form, but it could be written in the form, or any of them could be changed to be in this form. A times x plus b is less than c, where a is not equal to 0. And right there, I arbitrarily chose the less than or equal sign, but over here I just make the note that any of the four inequality symbols could be used instead of that. For example, I could say ax plus b is less than or equal to c, ax plus b is greater than c, etc. So the solution set of a linear inequality is the set of all of the values of the variable that make the linear inequality true. So let me just give you an example of this. If I say x is less than 5. Well, clearly, let's think of how many values of x make this true. If x is equal to 4, that's a true statement. If x is equal to 3, it's a true statement. If it's equal to 2, 1, 0, and the list goes on. And there's a lot of any value in between 2 and 1 would work. Any value in between 2 and 3 would work. So in general, it's often the case that the solution set of a linear inequality is infinite in size. So we have to figure out a way to actually write those, and let's do that now. So this is just down on my first page. What I did is I just copied it here. I'll eventually get it right. So here's our set notation. And what we want to do is draw a graph of that notation. And so this is a set. Remember, sets are always included in these curly braces. When I show x, x is just some real number. This vertical symbol here means such that x is less than a. So this set contains every real number x such that those real numbers x are less than a. This set here contains every real number x such that those real number x are greater than a. This set contains every real number x such that those real number x are less than or equal to a, etc., etc., etc. This one down here, this set contains every real number x such that those real number x are greater than a but less than b. And here, this set contains every real number x such that those real number x are greater than or equal to a but less than b. And this is the set notation. We have a graph that can depict the exact same information, and then we have what's called interval notation, which is just another way to express and denote this set. So remember, an interval notation is really just a set of numbers. So what I always do for these is, okay, let's just draw here someplace arbitrarily. Why is that there? I'm assuming I can draw here. Let me get my drawing tool back. Maybe I can't use this. My drawing tool back? Yeah, I drew right there. You all saw it. I'm going to make it a little bit smaller. So see, can I draw? I may not be able to draw. Well, let's do this then. So I'll just use this as reference. I thought in the past I was able to draw on these. That's okay. So let's just do the first one here. We'll just do it this way. We'll turn off this layer altogether. Get us some new drawing space. Go up here. Do this. Do this. And we're almost as good as before. Maybe better. I can actually. So now I should be okay. So the only thing I'm going to do now is just repeat this here. Put my arrow. So this represents the number line. So I want to draw x such that x is less than a. So it doesn't matter where you put it. Just to note a is somewhere on that number line. We don't know if a is greater than or equal to 0, so it doesn't matter. And what I want to do is I want to color in the areas of the number line that make this a true statement. But notice that x has to be less than a. So to denote that x is less than a, I'm not going to do that. I'm just going to freehand a circle instead of try to make it all fancy. I write a circle right there. That indicates that a is not included in the set. And then, however you want to do it, you can just squiggly line all the way down this way. And this denotes, and it goes on and on forever. That's what that arrow denotes. And the x's live down here. So this graphically denotes the set of all numbers x that are less than a, because when you go left on the number line, you're less than a. And the circle right here, which I've made larger and exaggerated, means that a is not included. Now we want to do the interval notation for that. So the interval notation basically is going to be this way. So if I have down here, this is minus infinity. Then I have all of this information here until I get up to a, and a is not included. So to indicate that a is not included in my interval, I write, it's called a half open interval sign. And infinity, that's not a number, so it's always enclosed this way too. So I'm almost there, but the interval, I don't put all of this wiggly stuff in there. I just write it is minus infinity to a. I replace all of that wiggly line with an a. So notice that this symbol here, which is in set builder notation, is exactly the same, gives you the exact same information as this, which is in interval notation. And this is the number line notation. And they all tell you the same exact thing. So let's kind of a little bit verbose there, but I wanted you to get the main drift. So here again I'm going to draw my number line, and the arrows indicate that it goes on forever and ever. I'm going to arbitrarily say a is right there. This goes on to plus infinity, and of course this goes on to minus infinity. So what's inside the set? Real numbers that are greater than a, but they don't include a. So since they don't include a, I'm going to write a little circle there, an open circle. And I'm going to squiggly line that. You could use a different color. And again, I want to indicate that a is not included, and it goes all the way to infinity. And the infinity symbols are always enclosed in the half open. So this is called, this symbol right here is called half open. Well, I don't guess it's called half open. There is no half. It's called open. It's just open. And this is called an open interval. And I'll show you the closed interval in just a second. So we did that one, we did that one. So I'm just going to do, I'm not going to do all of these. You can look in the book because I don't want to make this too big, but you will need to use this notation. And there's really nothing to it once you kind of get what's going on. It's not hard at all. So of this pair, I'll do this one right here. There's no need to do both of them. But this includes a less than or equal to sign. So again, what I do is I decide, well, I'm going to say A is right here, and this is all numbers x such that those numbers x are greater than or equal to A. So remember, this goes to minus infinity, this goes to plus infinity. So numbers that are greater than or equal to A are on the right of A. But in this case, they actually include A. They're greater than or equal to A. So to indicate that A is included, I write my circle, but I fill it up. It's a filled circle. I should have just freehand filled it up. So to indicate that A is included, we write what's called an open interval sign. And the squiggly lines here are just replaced by comma, and we go there. So this symbol here is called an open, this is called the open, and this symbol here is called closed. So this particular interval is half closed and half open. Let's just do one more example, and we're going to go on to, all of these are written out in the book. Yeah, let's do both of these last ones. Maybe we'll just do these two right here. And if you're okay with this, of course, I'm assuming you've already skipped ahead, that's the cool thing about a video. You don't have to be bored in class when I'm explaining something that you've got. For those who want to see more examples, that's absolutely fine. Here I'm using x, and x is greater than A is less than x, and B is greater. So here, these are all numbers x, such that x is greater than or equal to A. So A is included, but B is not, because x is less than B. So those are my not included, included, and it contains everything in between. So this would be denoted as closed, open. So this is an interval that contains A and all numbers greater than A, not including B. And this one down here, the next one below it, I've got to do a straight line here. In this case, I'm going to put my A and my B. It doesn't really matter where, but A is on the left and B is on my right. X is in between them. There is no, when I put the X there, that's probably misleading. The X are all of these numbers. I just wanted to show that X is between two numbers, but all of these squiggly lines, X could be here, or right where I put it here, or here. And in this case, these are numbers x that are greater than A but not including A, less than B and including B. So all of my x values are in here, and that is half open on the left, closed on the right. Okay, good enough. And if you need some more examples, just look at the textbook. So let's graph each set on the number line. Again, we're not going to do all of these, but I'll do a few of them so you get, because I think it's really easy and I don't want this video to be too long. If you have problems, you already know what to do. If you contact me during office hours, or if you can't during office hours, you can set up a time to contact me on Teams. I am able to bring up, I say I'm able to, I wasn't able to last semester, but they've made things better this time. I should be able to bring up a whiteboard and talk to you, literally voice over IP, and duplicate office hours just as much as we could. So we're gonna be doing these. Let me see the instructions here. We're going to graph each set on the number line and write this in interval notation. So just a few of these. Here's my number line. And if you want, you can always remind yourself that over here it goes all the way to plus infinity and all the way to minus infinity. We say all the way. Those aren't actually numbers. And these are numbers x, such that x is greater than 2. So I'm just going to say 2 is greater than or equal to 2. And it's included. 2 is included. So I fill in the circle. And I just squiggle. If you really like to color, you could just color that side of the line. Or you could indicate that x is there. By the interval, 2 is included. The infinity symbol, they're never included because infinity is not a number. So this is the number line, and this is the interval notation. Let's do another one. So you probably should, if you're following this and you're not bored and you've not jumped ahead. Try to do this one on your own. It doesn't matter where you put your minus 1. So this is all real numbers that are less than minus 1 but don't include minus 1. So minus 1's not included. So I'm going down this way. So minus infinity, this is the interval notation. Minus 1 is not included in the set. Do one more of these. Yeah, we'll do number C. That's good. That's the type I was looking for. So I have 0.5 somewhere and 3 somewhere else. And this is all numbers greater than 0.5, but not including 0.5, but less than or equal to 3. So it's all of this stuff right in here. Interval notation, half open, half closed. Okay, so let's go about with our second objective, which I'm pretty sure now is going to be using the addition property to solve linear inequalities. So the addition property for linear inequalities. So the addition property of linear inequalities is exactly like the addition property for equalities. If I'm not even going to write it down, I'm just going to explain it to you in words because it's so easy. If I'm given a linear inequality, I can add or subtract any number to both sides of the inequality to make it true. So here's the cool thing. When you're given a linear inequality, You can almost pretend, there's always that one little exception, you can almost pretend it's an equality and go about your business solving it, treating the inequality symbol just as if it were an equality symbol. But there is one exception and we have to deal with it, but there's always ways we can get around it. And that exception is when you multiply. So I want to isolate x, so I'm going to move my minus 2 to the other side. When I do so, it has to pay a price, and the price is it changes its sign. So this is x is less than 7. And it says write your answer in interval notation. So this is all numbers less than 7. So I go all the way down to minus infinity, but 7's not included. So I have to indicate that by my open interval sign. So that's not so bad. Let's do another one. Really quite simple. So this is example 2b. 3x plus 4 is greater than or equal to 2x minus 6. So what I'm going to do is I'm going to move, I always kind of want to keep my variable term positive. So that means I'm going to move the 2x over to this side. In other words, I'm subtracting 2x from both sides. And I'm going to move the 4 over to the other side. So the minus 6 stays there, and the 4, when it moves over, pays the price of changing sign. So 3x minus 2x is x, and that's going to be greater than equal. Minus 6 minus 4 is minus 10. So that means all values of x greater than or equal to minus 10. Since minus 10 is included, it's supposed to be an infinity sign, then I use that symbol. So if you're kind of, there's some trepidation here, just go back to our regular, what we did before, and derive the interval notation from your, this is minus 10, and this is positive infinity. 10 is included. So you literally just derive your interval from reminding yourself of what it looks like on the number line. We have 3x plus 1 is less than or equal to 2x minus 3. Again, for reasons which hopefully will become apparent, I want to keep the coefficient on my x term positive. So I'm going to move, it's like I just did this one. So I'm going to move the 2x over. It becomes minus 2x. And that means the plus 1 has to go over to the other side. The minus 3 is already over there. So 3x minus 2x is x. Minus 3 minus 1 is minus 4. So this is x less than or equal to minus 4. So all of these numbers are going all the way down to minus infinity, and it includes 4. On the number line, I'll say that's minus 4. Minus 4 is included, and it goes all the way down to here. Right here's minus infinity. So now you can see exactly how I got this interval notation. So the multiplication property of inequalities. So here is the deal about the multiplication property of inequalities. So we'll go ahead and write this out symbolically. I'm going to tell it to you. So here we go. I guess I probably should have written this earlier, but let A, B, and X be any real numbers. Where B is greater than 0, then X less than A. So when I use the less than there, you could use any of our four inequalities. You can use any four of our inequality symbols. Then X less than B. Wait, B is greater than 0, so I don't want it to be a less than B. X less than A and BX less than BA are equivalent inequalities. What does that mean? It means that their solution sets are the same. So here I'm just going to explain it to you in English. So as long as your number B is greater than 0, then you can multiply both sides of your inequality by B and nothing changes. But on the other hand, when B is less than 0, we have the following: X less than B and BX. Notice what I did there? I flip the sign when B is negative. And of course, if B is 0, they're not equivalent inequalities. So here's the deal. When you have to divide or multiply by a number, if you're multiplying by a negative number less than 0, you have to remember to flip the sign. And I'm anticipating some questions. If my original sign is less than or equal to, its flip is greater. So if my original sign is less than, its flip is greater than. If my original sign is less than or equal to, its flip is greater than or equal to. So let's just use some examples, and it's really not that bad. It's just something you have to remember. Makes complete sense though. Oh good, we have one with fractions. Super simple fraction. Nothing hard about this at all. So this is 3a. I have x divided by 4 is less than or equal to 3/8. So what do I say? We treat these just like they're equations. They're inequalities, not equations. So I find the least common denominator of 4 and 8. And the least common denominator of two numbers is always greater than or equal to the larger of the two numbers. And it's equal to the larger of the two numbers when the smaller of the two numbers evenly divides the larger. 4 evenly divides 8 because 8 divided by 4 is 2, which is a whole number. So the LCD is 8. So I'm going to use the multiplication property and multiply both sides by 8. Now 8 is positive. It's greater than 0, so I don't have to worry about any sign flipping. So 8 times x divided by 4 is the same as 8 divided by 4, which is 2 times x. So that's 2x. I just bring down my inequality symbol unaltered. 3/8 times 8 is the same as 8 divided by 8, which is 1 times 3. Okay. Now 2x is less than or equal to 3. I want to know how much 1x is. So now I'm going to divide by 2, which is the same as multiplying by 1/2. 1/2 is greater than 0. So I don't have to do anything with the inequality symbol. So that gives me 2x divided by 2 is x. X is less than or equal to 3/2. So we want to write this in interval notation. Yeah, you need to know interval notation really well. It's really important. One of the reasons this is done is because for those of you who are going to go on to calculus or STEM majors, you'll eventually get to calculus, and that's an area of math called analysis. And intervals are used, and they're really important. So again, if you have a doubt, sketch your number line really fast. This is minus infinity, this is plus infinity, here's your 3/2, it's included, it's all of this stuff down there. So let's go to another example. I'd rather do the fractional one. Let's look at this one really fast, though. There's nothing about it that's difficult, but I do want to show you something. So you see, I want to show you a trick. So this is just going to be the trick. I'll probably end up just solving the thing. So minus 2.3x is less than 6.9. So it's ready to solve, right? I just want to divide through by the coefficient of x. But the coefficient of x is less than 0. It's negative. That means when I do it, I'm going to have to flip the sign. So let's do it. I have to divide through minus 0.23. And when I do that to both sides, I cannot keep the sign as it stands. I literally have to switch it. And that's a lot. I'm fearful that you'll forget. So this is my suggestion. Well, there's nothing that keeps me from moving the positions of these. If I move the minus 2.3x over to the other side, the price I pay is it changes its sign. And now if I move the 6.9 to the other side, the price I pay is it changes its sign. Now all I have to do is divide by 2.3. And I don't have to flip the inequality sign. Why? Because I'm dividing by a positive number. 2.3 is greater than 0. And I'm done. So if you remember to always just move, if the coefficient of your x term is negative, move it to the other side and the constants to the opposite side, and you have this, and you don't have to worry about flipping the sign. So this gives us that x, I told you I was going to go ahead and solve it, is greater than 6.9 times 2.3. We don't want that number, and I don't want you to get a calculator. So what's minus 6.9 divided by 2.3? I want to get rid of those decimals, don't I? So I'm going to multiply it by 1. 1 disguised in the form of 10 divided by 10. And that's going to give me 69 over 23. And it's negative. And that's more easy to do because it's clear that 3 times 23 is equal to 69. So the answer is x is greater than minus 3. So that's the final example. Okay, yeah, I always do that. I want to skip something and then I just end up going back and doing the whole thing. Well, there's some lessons to be learned there. In particular, the lessons that your habit to grab your calculator and let your calculator do your mental work. You know, in the end, you know, you hear a lot of discussion about robots taking over our jobs and artificial intelligence, which has already taken over many jobs. Well, there's a lot of things artificial intelligence can't do, and if you want to make sure that you can compete with artificial intelligence, the more skill levels you have, the better. So let's do 3c. So 2x over 5 is greater than or equal to 4 over 15. I'm going to show you another trick here. It's the cross multiplication trick. So what do I do to isolate my x term? I have to multiply both sides by the reciprocal of 2/5, or the multiplicative inverse, which is 5 halves. Because 5 halves times 2/5, when I cancel, they become 1s, not 0s, is equal to 1, and that's what we want. Another way to do this, and I did this all the time, is I just cross multiply. I multiply 5 times 4, the x stays there, and 2 times 15. So that leaves x greater than equal to 5 times 4 is 20, and 2 times 15 is 30, and how much nicer that is, because it's super simple to reduce. So those for you, the more formal way to do it is I have a linear inequality, 2x over 5 is greater than or equal to 4/15. What you do formally is you identify the coefficient to the x term. That coefficient is 2/5. So you multiply both sides by its reciprocal, also known as its multiplicative inverse, which is 5 halves. So let's do that. 5 halves. 5 halves is clearly greater than 0. So the 5's cancel, the 2's cancel, so that just leaves me an x over here by itself. That's what I wanted. 4 times 5 is 20. 15 times 2 is 30. And guess what? I get the exact same answer as before. Two different ways to approach that problem. So now we're going to combine a few steps. So here literally, I mean, everything we've done right up until now are baby steps. Our examples 4A, B, and C are something like you would see on the exam, and then 5 and C are word problems. So we're going to do all 4 of these, because this is, you're not going to see hardly any of the baby steps, because these examples combine everything. So this is 4A, and I'm given minus x minus 3 plus 2 is less than or equal to 3 times 2x minus 5 plus x. So again, we're going to simplify both sides as much as we can, collect like terms and simplify, and then we will move things across the equal sign as required. So remember, minus x plus 3 is the same as minus 1 times x minus 3. So minus 1 times x is minus x. So I'm just using the distributive property here. Minus 1 times minus 3 is plus 3. And then I have the plus 2, which I did nothing. It just used distribution again here. 3 times 2x is 6x. And then 3 times minus 5 is minus 15 plus x. So now let's collect like terms on each side. So minus x. 3 plus 2 is plus 5. And collecting like terms here, you can skip some of these steps if you want. So again, I'm going to simplify the right-hand side of my inequality. 6x plus x is 7x minus 15. So here you want to make the right choice. I don't want to deal with the possibility of flipping the inequality symbol. So I'm going to move the minus x over to the right-hand side, and it becomes plus. So that's going to give me 7x plus x. And that's 8x. I want it to be positive. So that means I'm going to have to move the minus 15 to the other side, and it becomes plus. The 5 was already over there. So 5 plus 15 is 30, is less than or equal to 8x. 5 plus 15 is not 30, people. Sorry about that. 5 plus 15 is 20, last we checked, and that's less than or equal to 8x. So you have to divide through by 8. 8 is positive. So that gives us, you don't leave it in that form. Your final form should always be x is greater than or equal to whatever the inequality is, some number. So 20 divided by 8 is less than or equal to x. And we want that reduced. So 4 divided by 20 is 5. And, 20 divided by 4 is 5. And 8 divided by 4 is 2. So 5 halves is less than or equal to x. In other words, 28 is the same as 4 times 5 divided by 4 times 2. And the 4's cancel, leaving 5 halves. So let's do 4b. Yeah, this one's rather long. It seems to me like I've been talking. It seems to me like if I were in a class, the bell would have rung, which is fine. That's the only good thing about teaching online. I mean, not online, I guess you want to call it, because that's what I'm doing. I'm just recording my lectures. I don't see any of you. Hi. But of course I don't see you. So again, we use, what are we going to use? This is a fraction. So my only denominator is 5, so the LCD of 5 is just 5. Now I can put denominators and say 1, so I'm going to multiply both sides by 5, the entirety. So 5 is going to be multiplied by the entirety of both sides. Since 5 is greater than 0, I don't have to worry about flipping the inequality. So 5 times 2/5 times x minus 6 is the same as 5 divided by 5, which is 1, times 2 times x minus 6. So the left-hand side is 2 times x minus 6. And this is 5 times x minus 1. All I did is I just used the commutative property that when we're talking about multiplication, a times b is equal to b times a. So x minus 1 times 5 is the same as 5 times x minus 1. So I'm hoping you're going to see now I'm going to use the distributive property. 2 times x is 2x. 2 times minus 6 is minus 12. 5 times x is 5x. 5 times minus 1 is minus 5. So now I have to make the decision. I want to move my 2x to the other side. That's going to keep my coefficient to my x term positive. So that means my minus 12 stays there. That means the minus 5 has to move to the other side. The price you pay is it change its sign. 5 minus 12 is minus 7. It doesn't matter that that's minus, because there's no x term involved. And 5x minus 2x is 3x. So my coefficient to my x term is positive. So no flipping of inequalities. So I'm going to divide both sides by 3, and I get minus 7/3 is greater than or equal to x. And I should be writing these in interval notation. I'm sure it asks for it. So here, minus 7/3 is greater than or equal to x. Let's just, when in doubt, do a number line. I have minus 7/3. And it's included, and it's greater than x. So x is down here, and my minus 7/3 is greater than x. And all of this down here is my solution. So the solution is in the interval format is that. There's another and perhaps easier way to do it. I hope that you can see when I say that minus 7/3 is greater than or equal to x is exactly the same thing as saying x is less than or equal to minus 7/3. These two statements are equivalent. So this is 4C. I'm challenging you to do this one on your own. Once you see what the problem is, which you can see right now by pausing the video, go ahead and pause it, get out a pencil and piece of paper and write it down, and see if you get the right answer. You should be doing that a lot. That's the best way to learn. So I'm going to go ahead and work it out. So again, we have a denominator. So my LCD is really 5 and 1. And what did I say earlier? Because all of these can be written as fractions, I can just put 2x over 1 and 1 over 1. I don't change the value. If the LCD of two numbers is always greater than or equal to the larger of the two numbers, and if the smaller of the two, which is 1 in this case, divides the larger, then it's the larger number. So basically, I'm literally going to multiply the entirety. I want a different color here. These parentheses right here are really important. I want to multiply the entirety of both sides by 5. As the number one mistake I see at this level is you'll get the left-hand side right, but you'll just multiply, the right-hand side is made up of two terms. 2x, that's one of the terms, and 1 is the other. But you have to multiply both of those by 5, so you need to put them in parentheses. So 5 times 3/5 times x minus 3 is the same as 5 divided by 5, which is 1 times 3 times x minus 3. And if you're just used to just canceling out there, that's fine, but you have to understand why you're doing it. I see a lot of canceling out that doesn't make any sense. So here I'm going to use distribution. 5 times 2x is 10x, and 5 times 1 is 5. Not quite ready yet because I still have to use distribution over here. 3 times x is 3x, 3 times minus 3 is minus 9. And here we want to make a choice that will make this better. I want my variable term, the coefficient, to be greater than 0, so that means I need to move the 3x over to this side. In doing so, it becomes negative. That means my minus 9 has to be joined by a minus 5. Minus 5 minus 9 is minus 14. 10x minus 3x is 7x. It doesn't make any difference that the constant term is negative because I'm dividing through both sides by the positive number 7. So that gives me minus 14 divided by 7 is greater than or equal to x. But minus 14 divided by 7 is minus 2. So minus 2 is greater than or equal to x. That's the same thing as saying x is less than or equal to minus 2. And in interval notation, I start at minus infinity until I arrive at minus 2, and minus 2 is included. So 2 more problems left. So this I've been skipping my objectives. This is the final objective, solving problems modeled by linear equations. Word problems, they like to use the word modeling because that's literally what we do. I mean, if we have hurricanes stirring up out in the Atlantic or the Caribbean, computers use math to model where they might arrive in their probability cones. So a salesperson earns $600 per month plus a commission of 20% of sales. Find the minimum amount of sales needed to receive a total income of at least $1,500 per month. You might very well be offered a job and you have to solve something very similar to this. So the first thing I want to note is the word minimum means at least, you want to earn at least $1,500, but more is clearly okay. So let's find out and just do this into, so total monthly income. You want that to be greater than or equal to $1,500. So it's got to be at least, at the very, very smallest amount it can be, is $1,500, including $1,500, but more is okay. But your total income is $600 plus 20% of sales. And that has got to be greater than or equal to $1,500. So 20% of sales, what is it we're looking for? Let X be the sales amount. That's what we're asked to solve. I should have probably written that down earlier. So now I can translate this. The word of means times. So now we can literally translate this directly into an inequality. So I have 600 plus 20%, so that's 20 over 100, of turns into multiplication. Cells is my x, is my unknown, has to be greater than or equal to 1500. So I'm going to do this a different way. I could multiply both sides by 100. Let's just go ahead and do that. That's how we've been doing it. So I'm going to multiply both sides by 100 because that's my denominator. So when you multiply both sides by 100, you just take the existing quantity. Well, you've got to use distribution over here. But in one direction, it's going to be really quite simple. You take the existing quantity and just add 2 zeros. So my 600 times 100, I just add 2 zeros. So it becomes 60,000. And here, 100 times 20 divided by 100 times x is the same as 100 divided by 100, which is 1 times 20x. So that's just 20x. And here, to multiply 1500 divided by 100, I just add 2 zeros. So again, I don't have any choice. I want my coefficient term on the x to be positive. So it stays on the left-hand side. And my 60,000 moves over to the other side and becomes negative. So that gives me 20x is greater than or equal to 900. So I'm going to divide both sides by 20. And I get x is greater than or equal to, it's 9,000. X is greater than or equal to 900 divided by 2, which is this? Sorry, people. I'm just kind of doing things in my head. Let's go over here and do this. Zero, 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 zero. There we go. I'm missing a 0. Okay, now I'm right. There we go. So it's 90,000. So now I'm going to divide it by 20. So now I can hack off those 2. So then I have 9,000 divided by 2 is $4,500. I'm going to talk about what just happened there in just a second. So my sales have to be greater than $4,500. How did I realize that I had done something wrong over here? It's because literally when I did the math, I was getting x is greater than 45 or x is greater than 450. And I know if I'm going to make it a minimum of $1,500, I have to sell more than 450. So it's the very last part of the reading problem steps I did a few lectures ago. That basically your variant answer you have to check conceptually. If conceptually it doesn't make any sense, you know you've made an error. And I apologize for that. I'm just lazy sometimes, and I just don't want to do things. You get mathed out. I know y'all get mathed out all the time, I'm sure. But sometimes I get doubly mathed out. And I love math, so that's kind of hard. So this is example number 6. In the U.S., the annual consumption of cigarettes is declining. So that means it's going down in number. The consumption C in billions of cigarettes per year since 2004 can be approximated by the formula. So C, that's the number of cigarettes in billions since 2004, is C is equal to minus 11.8 times T plus 390. So this is a linear equation. That's an equal sign right there. And T is the number of years since 2004. So if T is 1, that means we're 1 year since 2004, we're in the year 2005. So use this formula to predict the years that the consumption of cigarettes will be less than 200 billion per year. So what we want is C is the consumption in billions of cigarettes per year, and we want that consumption to be less than, and this is the consumption over here, we want it to be less than 200 billion. So really the only part about this is deciding which direction the inequality is. So it's really common to put the linear inequality that way. But you have to realize this actually gives the amount per year, the right-hand side. And we want that amount per year to be less than 200 billion. So that's how it works. So here again, this is a linear equality in the variable t. I want this minus 11.8 to be positive. So I'm going to move it to the other side. And that means the 200 has to come to the right-hand side, and it becomes negative. So that gives me 11.8t is greater than 190. Now I'm going to divide through by 11.8. 11.8 is a positive number. And I get t is greater than 190 over 11.8. Now the cool thing here is we kind of want to know a real number, but if this was a test you would not be allowed to use calculators. The only thing that I would want to see here is this as an actual fraction, so I want the numerator and denominators to be whole numbers. So how do you do that? I move this number over, the decimal place over by 1 is what I need. So in order to move it by 1, I have to multiply the fraction by 1, but 1 is going to be disguised as 10 divided by 10. So that gives me t is greater than 190 times 10. I just add a 0, and 11.8 times 10, that allows me just to move the decimal place over. And of course, if you had time, you would reduce that. It turns out that that is about, t is greater than, let's just see, I'm curious, 1900 divided by 118. I have in my notes that it's a 16.1, and it is. So t is going to take about 16.1 years for that to occur. Okay, that's it for 2.4. If you have any questions, just hit me up in Teams.